then we'll explain it to you. So just don't know when you explain the composite beam. No, that won't happen. Yeah.
For the ECI and the EC, are we expected to like find those ourselves, or will it also be given?
Most probably it's given to you. If it's not given to you and you don't have the required values or you don't have the formula, you can always ask us.
Okay.
Yeah.
So we don't get, that long equation of like 4 million times.
4 million times? Which equation is that?
No, that's
It's 57,000.
No, there's another equation. That's not
For EC?
Yeah, like there's that range when it's aged or something.
It's 40,000 plus a million. It's when it's greater than 6,000.
Yeah.
No. Don't worry about all those things. No. If you think you need a formula, you can always ask us because we are not checking whether you have written the formula or not. Okay? Yeah. But then just don't come and say, okay, give me the equation 1 through 4 for the Yeah.
So if we're doing instantaneous deflection without the preach being included, but we're still including whatever.
Instantaneous doesn't mean it's at the right after stress transfer. Instantaneous means as soon as the load is applied. So that load can be applied right after stress transfer, or I could apply that load at service condition.
Okay, so then like the usage of ECI or EC never changes.
No, it never changes whether it's a long term or a instantaneous reflection. So next thing what I was going to do is continuous beams, right? So until now, what we have done before the continuous beams was all determinate beams. In case of determinate beams, the good thing is if you are asked to do a moment, the load balancing method, what you can simply do is you can say F times E naught or minus F times E naught is the moment at the cross section. F minus F E naught at the cross section equal to the moment at the cross section, and you could actually do the moment, the load balancing method to find out your F E naught and all those things. In case of a continuous beam, the problem is let's say if I have a beam which is not a determinate beam right now, and my strand profile looks something like a parabola for some weird reason. So in this case, we know that okay, this parabola is the parabola will actually create a equivalent load which is similar to a distributed load, W equivalent, which is given by 8F delta M over L square. I'll define what delta M is. In this case, what happens is if I replace this pre-stressing force and the eccentricity with its equivalent load, and if you apply it on this indeterminate beam, the moment profile or the moment diagram that you get is not the same as minus F times E naught. And that is due to the fact that you have some secondary moments M2. So in case of an indeterminate beam, what actually happens is the total moment due to the pre-stressing force and the eccentricity is the sum of the primary moment M1, which is same as minus F E naught or minus Fi E naught, depending on whether you are looking at the initial condition or the service condition, plus a secondary moment M2, which is simply due to the fact that the beam itself is an indeterminate beam. So in the previous case, when we had a determinate beam, the total moment due to the pre-stressing force was simply minus F E naught, that's it. But in case of an indeterminate beam, we have this extra term of M2. So what we need to actually do is find out this total MF, M1 and M2 to actually do the load balance. So this MF is nothing but the total moment due to equivalent loads. So if I'm given this beam, indeterminate beam, and if I have a parabolic tendon, what I'll do is I'll remove the parabolic tendon, I'll remove the F, and I'll replace it with its equivalent load, which is a distributed load. And if I draw the bending moment diagram, or the moment diagram for this case, it actually gives me my MF, that is my total moment, due to the preceding force and the E naught. So what you do is you remove the F, you remove the E naught, replace it by the equivalent loads. For a parabolic tendon, it's actually a distributed load, which is given by this formula. You apply that equivalent load on your beam, analyze it, and that actually gives you your total moment MF. Once you have MF, M1 is always minus F times E naught. You know the preceding force, you know the eccentricity. So you can calculate the value of M1. So my M2 simply becomes MF minus M1. MF you get from analysis, M1 you get by simply minus F times E naught. Okay. So in our case, what will be given to you is a beam, a continuous beam, and you're supposed to actually design for Fi and the E naught, and maybe check the moment capacity and the shear capacity and all those things. So you have to do a design that we have done previously, but in this case, it's actually an indeterminate beam. So again, depending on what kind of profile that you need to provide, so let's say we have to do the load balancing to find out your Fi and E naught. Let's say it's an indeterminate beam. And in the problem statement, it will tell you, okay, what is the actual load that needs to be balanced due to the preceding force and the eccentricity. So it can say that, okay, you need to balance a distributed load on this one, a point load on this, distributed on this one, and some weird load on this one. Okay, we won't give it to you in the exam, but let's say it's given this way. So I know that in order to balance a distributed moment, I need to provide a parabolic tendon in this span, right? In this span, since it's a point load, I need to provide something which has this kind of a tendon profile. Again, for this one, I need to provide a parabolic tendon. And for this case, I don't have a parabolic tendon. Most probably it will be actually a tendon which follows a cubic equation instead of a quadratic equation. So what you actually want to do is you want to actually find out what is the preceding force and what is the actual tendon profile that you need. The only thing that you know is your E naught MP. That's the maximum possible eccentricity that you can provide. And you know the balanced loads. So if you look at the equation for this parabolic tendon, right, you have the omega equivalent is equal to 8F times delta M over L square, where this delta M is the distance from the line connecting the two ends of the parabola to the actual location at the midspan. and this delta M is always and always defined at the midspan. So delta M is actually not E naught at midspan, it's the distance of the tendon from the line connecting the two ends. So if these 2 points are at a different height, your delta M will not be actually equal to E naught unless and until they both are at the 0 location. Okay. So this is my omega equivalent. Similarly, I can have an equation for omega equivalent for this one. I have an equation for this one. I don't know what is the equation for the cubic one, so I will remove this. Now what you need to do is you need to find one pre-stressing force which will be the same for all the spans, and only thing that you can vary within the span is your E naught, because you cannot vary the pre-stressing force between different spans, because once you fix the pre-stressing force in one span, it's the same force through for all other spans. So what you can do is you can write omega equivalent in, let's say, span 1. This is equal to 8F delta M of span 1 times L1 square. I am saying L1 because the length of span 1. Similarly, I can write omega equivalent of span 2 is equal to 8F delta M of span 2 times L2 square, and so on and so forth for each one of the spans individually. Now what? Say it again. Say it again. So once you have this equation for the equivalent load for each one of the spans, now what you need to do is you need to relate this delta M for each span to its E naught, because what you have is a limit on the E naught, not delta M. So what you do is you assume a tendon profile, and in order to assume a tendon profile, you can assume that the tendon profile will be similar to the moment profile due to these equivalent loads. So if the moment profile due to the equivalent load is, oh man, let's make it just uniform. Yeah, I don't want to do that. Yeah. So in this case, my moment profile actually looks something like, it goes to positive. I have 4 spans, right? So this, and goes this way. So the only thing that you know is the tendon profile looks similar to the moment profile. It's not the same as moment profile. It's not a scaled version of the moment profile. It just looks like a moment profile. That simply means that, okay, if this is a parabola, the tendon will also be a parabola. If the moment profile is a straight line, your tendon profile will also be a straight line for that particular region. That's it. It's not a scale version, it's not anything, it just gives you the shape. So now what you do is, let's say in the problem statement, since at the ends you know that the moments is 0, so you actually want to provide a 0 E naught at the ends. So you provide 0 E naught. If you look at the assignment, in the assignment it was given that what these values are. Actually, I'm dealing with 4 span. So in the assignment, actually this value was already given as, I remember, minus 1.57 E naught at the supports. But let's say it's actually not specified what is the eccentricity at the support location. What you can always do is you can actually maximize these values. You can put these as far as you can go on the beam. Okay. Now what you need to do is you need to find out what is the actual profile in all 3 of them. Now based on the omega equivalent, I know my F is the same. If my omega equivalent is same on each one of the spans, that means that my F times delta M of span I divided by Li square is actually a constant value, right? Because for each one I have the same equivalent load. Since F is also same for each one of the span, that means my delta M for span divided by the length of the span square, that has to be a constant value. If your span length is also constant for each one of the span, that means delta M has to be constant for each one of the spans, right? So if you look at the assignment, your span length was constant, so that's why you can just directly compare the delta m's. If your span length is not constant, then your delta m divided by L square is a constant value instead. Now I need to define this delta m as a function of E naught. So if I just look at this one, so this is my centroidal axis. I have already assumed what this value is, so I'll maximize it in the negative direction. The delta m for the first span is this height, and E naught is this, E naught at mid span, right? And this total height is delta m. So for this case, my delta m is nothing but this small height, let's call this h, plus E naught at m. The good thing is, if this point is fixed, let's say as in the problem assignment, let's say it's 6 inches. Okay, since you have already maximized this height, you know this is 6 inches, so you know this is actually 3 inch. Because this height is always calculated at the mid span. So this is 3 inch, this is E naught m, so I have delta m equal to 3 plus E naught m. Right? Now I look at this span. For the second span, my tendon profile looks something like this. In this case, my delta m is from the line connecting the two ends of the parabola. So this is my E naught m2, and this, this is 6 inches, 6 inches. So this actually becomes 6 inches. So delta m for span 2 is actually 6 plus E naught of E naught m of span 2. So now what I have is equation which correlates delta m for two spans with their corresponding eccentricity at the mid spans. What you have is a condition which says that neither this nor this can be greater than E naught MP. You have a limit on E naught, right? So if this cannot be greater than, let's say, 12 inches, this cannot be greater than 12 inches, that means this cannot be greater than 18 and this cannot be greater than 15, right? Because the limit on E naught is the same for both of them. So this cannot be greater than 15, this cannot be greater than 18. So I go back to this equation. This is a constant value, this is a constant value. I know what is the maximum allowable for each one of them, delta m, right? So if I maximize this, what you are trying to do is you are minimizing the value of f, right? Because the multiplication of f times delta m has to be constant for each of the spans, if L is the constant for both of them. So what you want to do is you always want to minimize the value of f. That means you want to maximize the value of delta m. So you'll plug in the value of delta m for two different spans. So for the first one, you'll plug in 15 inches. For the second one, you plug in 18 inches here. You calculate the value of f. Most probably 99% of the time, you'll actually get two different values from both the spans. Let's say you get 500 kips from here, and you get 400 kips from this one. So in order to make E naught equal to the maximum possible, you need 500 kips. And on this span, in order to maximize this, you actually need only 400 kips. That means if I increase this value of f for this second span, I'll decrease the value of delta m, right? Because the product is constant. Am I allowed to decrease the value of delta m? No, it's not. The tendon profile is not fixed yet. You are trying to find out what the tendon profile is. But are you allowed to decrease this delta m, or are you allowed to increase this delta m?
Decrease.
You are only allowed to decrease it because this delta m currently is assuming the maximum possible E naught. So since you cannot increase your E naught, you cannot increase your delta M. So what you do is you pick the larger value of the F that you get from all the spans. Yeah.
If you want your WQ to be the same for everything, though, didn't you say that the delta M has to be the same for everything?
Yeah.
So why don't you just pick the smallest delta M?
You pick the smallest delta M. Let's see. Okay, so what you are actually saying is this has to be equal to this, right? So 3 plus E naught M of first span has to be equal to 6 plus E naught M of the second span, right?
No, it's just saying pick the smallest one because you can't pick the biggest one to go.
You pick the.
Oh, E naught.
No, but how do you decide on which span do you actually maximize it?
Well, you can't pick 18 for both spans.
No, I can.
No, you said you
For delta M, I can make them both 18. I cannot make E naught to be the same, but I can make delta M to be the same because there is a difference in this constant. So if I pick this as 12, right? And if I pick this as 9, the sum of both two are actually 15. That is 3 plus 12, and this is 6 plus 9. So I actually have to make delta M to be constant if your span length is constant, assuming the span length is constant. If your span length is not constant, then you are actually equating delta M over L to be the same for both the spans. So that's what I'm trying to say is maximize both the delta M's. You actually find out the value of F and pick the maximum F. So that automatically takes care of the fact that if you have a different span for a different length for different span, it is already accounted for when you are actually calculating the value of F. You can directly equate the delta M's if your span lengths are the same, which was the case in assignment. But let's say if this is 60 and this is 50, right? Then you cannot directly equate these two because omega equivalent is dependent on L1 and L2 also. So what I'm saying is maximize both of them. Use this formula to find out F from first span, F from the second span, and pick the larger one. So if you have 10 spans, you have 10 values of F, one from each span. You pick the largest F out of those 10, and that actually becomes your F, your final F. Okay?
Your largest
Yeah.
or your minimum?
Say it again.
Your largest or
Your largest.
Oh.
You pick the largest because the largest will satisfy each and every span. The minimum will only satisfy the one span from which it is calculated. It won't satisfy any other span. So if you look at the solution, in the solution I just compared these two, the delta M's. The only reason I am able to compare the delta M directly is because the L1 and L2 are the same. If L1 and L2 are not the same, then either you compare delta M over L1 square, or you calculate the value of F and then just directly compare the F values. Okay? Yeah.
So you're saying the reason why delta M over L is constant is because of W is a constant. W is a constant across all of them.
Yeah, if W is not constant, then again it's useful to first calculate the F and then compare the F's. Because the only thing for sure which is constant is the precessing force. Everything else in this equation can change. The span can change. The equivalent load which is balanced on each of the span can also change. It can say, okay, balance 90% of the dead load on this one, 80% on this, 80% on this, and 90% on this one. Which will be pretty weird, but you can have a different omega equivalent also. So just to be safe, it's always easier if you just calculate the F for each one of the spans and pick the larger one. Okay. So now once you have the final value of F from comparing all the spans, now you can actually go back, put in the final value of F and calculate the actual delta M for each one of the spans. So it's kind of a repetitive process. Let's see. So what you do is maximize the delta M for each one of the span I. And then based on omega equivalent equal to 8F delta m over L square, you'll get the value of F. Let's call this J actually because Fi, excuse me. You'll get the precessing for one precessing force for all the spans. You pick max of F of J, and that actually becomes your final precessing force. Okay. Once you have the final precessing force, now you need to find out what is the tendon profile in each one of the spans based on this F. What you do is you go back to the same equation equal to 8F delta M over L square. In this case, when I was using this equation at this point, I was assuming the value of delta M and calculating F. When you go back, you actually have already found out what the value of F is, so now you are calculating the value of delta M. So now you get delta M for each one of the spans, and depending on how the strand is, whether it's non-zero at both the ends or it's zero at one end and different value at the other end, you can convert it to E naught at mid span for all the spans. Right? So you actually use the same formula, you use it twice. But first time you maximize delta M, find the value of F, and the second time when you come back, you already have the final value of F and you are calculating the delta M for each span. Once I have delta M for each span, I can find out the E naught for each span. And once you have the E naught at the mid span, you can actually define the actual profile. Yeah.
And then we also have like on the end spans.
Yep.
where you
Yeah. Just hold on a second.
the extra drop.
Yeah. So what Anthony is suggesting is saying is the one thing that you also need to account for is if in the at least in the end spans the maximum moment doesn't occur at the mid span. At least in the end span, it might not even occur for the other spans depending on what loads you are trying to balance. But until unless your loads are pretty weird, at least for the end span, the maximum moment will not occur at the mid span. So if the maximum moment doesn't occur at the mid span, what you can say is your maximum E naught for that particular span will also not be at the mid span. So what you can say is for this case, this E naught at the mid span is actually less than E naught MP. So when you are maximizing the delta M's for the end spans, you cannot put this E naught at the mid span to be equal to E naught MP. It has to be something less than E naught MP. Now, how less? You can actually start with 85% or 90%. You assume that okay, this E naught at the mid span for span 1 and let's say the last span, it's only 90% of the maximum allowable. Based on that, you'll do all these calculations and finally you'll come up with the final value for the E naught. And then what you do is when you define the final stand profile, right, you make sure that your E naught, the maximum E naught anywhere is still less than E naught MP. Because right now what you did was you just assumed a value at this point, which is the mid span, but it might actually drop down and increase further. So you still need to go ahead and make sure that the maximum E naught anywhere is still less than E naught MP. If that doesn't happen, what you need to do is you need to actually decrease this factor a little bit further. So let's say you started with 90% here, so you said it's 90.9 times E naught MP. You do all these calculations, you come back and you see that oh, if I pick 90% at the mid span, this actually becomes more than E naught MP by 1% or 2% or 5%, doesn't matter. So that means that this 90% is actually too big a number. So what you do is you decrease it to let's say 85%. Okay? Yeah.
I'm wondering also like realistically on a test. So say we're doing this part and then we finally create our 10 and 12 pounds to balance for equivalent load.
Yeah.
And then could he, like, do you think he would ask to calculate calculate MF, like the indeterminate structure, like
Yeah.
how far would we have to go to work on
Yeah, why not?
analysis?
If you know moment distribution, right, anything which is a continuous beam, anything less than 3 or 4 spans should be straightforward. 3 or less than 3 or 4 spans, it shouldn't take you too long to actually analyze it. Yeah. And I think he mentioned on Friday's lecture that okay, just go ahead and go back and look at your notes for moment distribution. Yeah.
So
So
also said like don't worry about, like I asked him if we have to worry about knowing all our like fixed end moments.
no, see what I see again. It's what I am thinking might not be true is that he won't ask you to actually use moment distribution because it doesn't make sense in this class to actually ask you guys to actually analyze some indeterminate beam because you have already taken so many classes on those things, right? So most probably you'll be given the moment profile, but if it was me, I'll still go back and look at like how to do moment distribution just in case. It's better to be safe than sorry. That's it. Yeah. So still go back because even if he asks you to do a moment distribution, it will be a very simple problem. It will be a super straightforward problem. It won't give you like 50 spans or something which takes like 3 hours to analyze the structure itself. Yeah. So most probably he should give you the moment diagram and stuff. Otherwise your structure will be super straightforward. Okay.
We could have done indeterminate beams using superposition as well, right? Did you get answers?
Indeterminate beam using superposition? How?
Oh, that's pretty important. You know, no, I'm talking about like
Oh, that's flexibility method.
what? Yeah.
Yeah, that's the flexibility method. Oh, you don't want to do that. Take that. The other thing in this case is so once you have the tendon profile, the next thing you need to do is check for the moment capacity, whether the nominal moment capacity is more than the demand. So normally what we have is phi times mn has to be greater than mu, which is the moment due to the factored loads. But in case of continuous beams or an indeterminate beam, you also have another term of m2. And this m2 is based on unfactored S, that is the effective pre-sheathing force. So this mu has those mu has the factors on all the loads, so it's 1.2 times self plus 1.2 times dead plus 1.6 times the dead load, so 1.6 times the live load. But this m2, which is the secondary moment, it's actually unfactored and it's due to the effective pre-sheathing force. And in the exam, be careful because it might say that okay, the load which is balanced, let's say it says okay 90% of the load is balanced by the initial pre-sheathing force, or it can say 90% of the dead load is balanced by the effective pre-sheathing force. Then what simply means is in this formula, in the first case this is actually Fi, in the second case it's actually F. So read the problem statement carefully. So it might say okay 90% of so and so load is balanced by the effective pre-sheathing force. Then this becomes F, that is eta times Fi. So whatever you calculate from this formula will be F. In the other case, it can say okay 90% of so and so load is balanced by the initial pre-sheathing force. In that case, this becomes Fi. Okay. And one good thing is if you calculate your total moment, your M1 and M2 based on either Fi or F, the other one is just simply related by the factor eta. So if you find out MF, M1 and M2 based on Fi, you don't have to do all those calculations again for F if you need it. You just multiply all these values by eta, you get the all these numbers for effective pre-stressing force. If you calculate it based on F, divide by eta and you get all the numbers for Fi, because it's still a linear system. So if you increase the load by a factor of eta or decrease by a factor of eta, your moments also scale by the same factor. Okay. What is? Oh, the stress check. Yeah. So for the stress checks, so until now what we have been doing is the sigma top is F over AC 1 minus E naught, this is top saying minus AB top plus M over ZT, right? This is the equation for the stress at the top for a normal case. The only difference for a continuous beam is that in this case you also need to account for the secondary moments, and how you account for that is just replace this by E naught star, where E naught star is defined as minus MF over F, where this MF is calculated based on the equivalent loads due to the effective pre-stressing force, or which is equal to minus MFI over FI, where this is calculated based on Fi. Because I can scale this by a factor of eta, and I also scale this by a factor of eta. Yeah.
The E naught star is for the thrust line, right?
Yeah, E naught star gives you the location of the thrust line. Yeah.
So what's the significance of the thrust line?
Thrust line is imaginary line which produces the same stress conditions if your pre-stressing force was only applied at that particular location. So what it simply means is, so normally what you have is a case, you have a pre-stressing force F at a distance of E naught, and you have a moment of M, right? External moment. What thrust line is saying is that the stresses produced in this condition is same as the stresses produced in a different condition where the pre-stressing force is applied at a different location. So that thrust line gives you the location of the equivalent compressive force on the cross section. So the stress produced by the pre-stressing force E naught and the external moment in this case is same as the stresses produced by this case where this is F and this is simply E naught star. Is the C line in determinate beam is same as the thrust line in indeterminate beams. So the only difference is your overall equation still remains the same. So if you are checking for the top, you use the equation for the top. The only thing is you replace the E naught by E naught star to account for that secondary moment M2. If you don't want to do that, then you have to do this, whichever you like. So either you account for M2 explicitly, or you account for M2 by E naught star. They both do exactly the same thing.
Okay, so the M2 is in the M, right? So that would be like an MF, and then the M2 is in that M.
Say it again.
So the way the M2 gets factored in to your E star is that in the M you
In the MF, yeah, yeah. Because MF is the sum of that minus F E naught plus M2. So this MF already contains the effect of the secondary moments. Okay. So I think the biggest confusing part in case of a continuous beam is to how to find out the pre-stressing force and the tendon profile. So what you do is you write down the equation for the equivalent loads which needs to be balanced. You maximize the delta M for each one of the spans individually. You will get 10 or 20 values of F depending on how many spans you have. You pick the largest value of F You go back, you use the same equation, but now you know the value of F, you calculate the value of delta M, and then based on the tendon profile, you can relate your delta M to the eccentricities at the midspan. And once you have the eccentricity at the midspan, you can actually define the entire profile. Yeah.
Just go ahead and run the tendon profile using the parabolic equations. That's exactly what you said.
Yeah, so when I mentioned that, okay, once you define the tendon profile, right, you need to find out, okay, what is the maximum what is the maximum E naught in the entire span. So in order to find out the maximum E naught, you need to find out the equation for the tendon. So what you'll have is, let's say, you know this value at the end, you already fixed this value, let's say 6 inches or minus 5.17. And what you have calculated is this value, E naught at the midspan, right? So since I know it's a parabolic tendon, so it has the equation E naught x ax square plus bx plus c, right? So I only need to define a, b and c. I can define the entire tendon. I need 3 equations. This is my first equation. At x equal to 0, E naught equal to 0. At x equal to L over 2, my E naught is, let's say, E naught M, and at x equal to L, my E naught is whatever, minus 6 inches or minus 5 inches, whatever you have fixed. So you get 3 equations in A, B, and C. You solve for A, B, and C. You get the actual equation for the tendon. You differentiate the equation. You get the location of the maximum. You find the maximum. Make sure it's less than E naught MP.
Yeah, but and if it's less than E naught MP, can't you just
No, it has to be less than E naught MP.
yeah, that's it.
Yeah.
Like, then that's it.
No, you need to make this check only for the spans where the tendon profile is not symmetric about the midspan.
Oh, okay.
Yeah, so if you look at the assignment, right, I didn't even check for the middle span because I know that and for the middle span the maximum E naught does occur at the midspan.
So is this just to find that assumption that we made is okay, or is this?
Yeah, to
find the
make
actual
sure
profile?
to make sure that it is actually okay.
So this is not like this is not the actual profile.
No, this is the actual profile if everything is okay.
Okay.
If everything is not okay, then you need to decrease this value to a smaller value and then redefine that.
Is there a safe assumption so we don't have to check it?
It starts with 85%. It will 85% of E naught MP. It will always work.
Okay.
Yeah, at least 95% of the time it will work.
Should we call you on that?
Huh?
Should we say you said it?
See, the thing is, no, you can use, if you want, you can use 75%. The thing is, in this case, you don't want to maximize the value of E naught. You don't want to maximize the value of, because it becomes much more tedious to make sure that maximum E naught is exactly E naught MP. So if the maximum is less than E naught MP, even if it's less by a couple of inches or something, it's still fine. You don't need to go back and revise it. So you can, if you are short on time, you can always start with 85%. Yeah. In the worst case scenario, even if it doesn't check out, it's not a big deal because this whole thing is a time consuming thing. You find out the tendon profile, you differentiate it, you find out the location of the maximum, you plug the values in, then you get the maximum value. Yeah, so it's a tedious task. So even if you don't check it, maybe like 1.2 points. Who cares?
You said no points.
Maybe no points. That depends. Depends on the problem, how big the problem is. But don't just say that, okay, I won't check it all. At least show some amount of work that, okay, you ran out of time or something. Just don't say, okay, I don't want to check it out. Then I have to take points off. Yeah. Or most probably the problem statement might even say, okay, you don't have to make sure. So on a safe bet, since you are short of time, start with 85% for the end spans where you know that, okay, it's not a symmetric moment diagram. Yeah. Like I think for the assignment, even if you pick 99% of E naught MP, it still checked out. Yeah. Yeah, for that particular problem, it even checked out for 99% of E naught MP at the midspan. Yeah.
The lower the right side.
Because I can actually lower this thing and make sure that, okay, I get a different tendon profile.
So he'd probably tell us what guys fix it out like right?
Yeah. See, the thing is, even if we don't tell you, you can at the support, you can always fix it at the maximum.
That could somehow limit those.
No, it actually doesn't limit you, because the higher this value is, the larger my delta M is. It doesn't matter whether you are in the end span or the mid span, right? So you maximize one and then you try to find out the other one.
You don't have to
Okay.
check the midspan. You don't have to check the midspan, do you? If you're gonna do
It depends on the moment profile. If the moment profile is symmetric in the mid span,
yeah.
you do, because since the maximum does occur at the mid span, you don't have to check it.
Okay.
If you say that okay, it's E naught MP, it will be E naught MP.
Okay.
Can we move on to these projects?
Yeah. What if you don't have any problems on composite, right?
What time does the bus stop go?
What time is it?
Like
What? Oh yeah, I take the Mesa. Yeah. Okay, for composite. Okay. So again, for the composite beams, what you need to find out is, given the composite cross section, given the cross section of the composite beam, you need to find out, okay, what is the Fi E naught that you can provide, and find out the moment capacity. So it's still straightforward. The only thing is, in case of a composite beam, the two parts of the beam, they are cast at different times. So first what you do is, you have the girder, that's the main part of the composite beam. You cast it, you pre-stress it, you do the initial stress transfer due to the pre-stressing load, and only after that you go ahead and actually top the beam with the slab or the next part of the composite beam. So in case of a So in case of a composite beam, it actually becomes important to look at, okay, how the composite beam is actually constructed. So there are two ways. The first one is unshored construction. The other one is shored construction. The difference between these two is, so what you already have is your girder, which is already cast at casting yard. So you already have the girder. So this is the cross section, let's say, and this is the beam. And what you need to do now is, you need to actually put a slab on top of this, which is the next part of the composite section. So in case of an unshored construction, what you do is, you prepare the formwork, because you cannot just drop the liquid on top of beam and expect it to make a nice thin slab. You need to provide some kind of a formwork to make that slab. The only difference is, in case of an unshored construction, this formwork that you have, which gives the slab a certain shape, it's actually connected to the girder itself. So if I apply any load on the formwork, it gets transferred to the girder in case of an unshored construction. So if I pour my concrete to cast my slab, so even though that concrete at that particular point is still a liquid or a semi-liquid, but it still has some weight to it, which has to be carried by something. So in case of an unshored construction, that extra load is transferred to the girder, so it will actually increase the moment on the girder itself. In case of a shored construction, you still have your girder, you still have your formworks for the slab. But in this case, the difference is that formwork is not connected to the girder itself. It's actually, let's say, it's seated on the surface. So if I put some weight on this formwork, instead of getting transferred to the girder, it actually gets transferred somewhere else. So in case of a short construction, when I pour my concrete, my girder actually doesn't see any increase in load. Okay. Now after that, what you do is, once you have poured the concrete, you wait 28 days for the slab to actually gain enough strength, and then you remove all your shoring, whether it's shored construction or unshored construction. You remove the shoring, and now what you have is a composite section where you have a girder which was cast at a previous time, and which might have a different F prime C or concrete properties, and then you have a slab which was cast at a later time, and it might again have a different concrete properties, F prime C, EC and stuff. And once you have this composite section, now you actually have the dead load, live load, and all the service loads which will be applied on this beam, right? So the two different, in both the different cases, if you look at the method of loading, so the first thing what we have is just simply the self weight of the girder, right? What part of the composite section is actually carrying this self weight to begin with? Initially I only have the girder, right? So it's only the girder which can carry its own load. So this is carried by girder only, and in this case also it's carried by girder, right? In this case, for the unshored construction, when I pour the concrete for the slab, what part of the structure is actually carrying that extra weight of the concrete for the slab? In case of a short construction, since it's connected to the girder, it's carried by the girder resistance. So M slab, that's the moment due to the weight of the slab. Again, this is carried by girder. In this case, for a short construction, when I pour the concrete, it's taken by something else. I don't care what it's taken by, because if it's directly connected to the ground, it directly gets transferred to the ground, right? So it's carried by something else. Now, at service condition, you remove the shoring, you apply your dead loads and the live loads. So you have additional load of dead load, and you have an additional load of additional live load. What is this load carried by in unshored construction? It's carried by the composite action. The same for this case, right? In this case, once I remove the shoring, and even if I don't apply any extra load, I don't apply MD and ML. Once I remove the shoring, where does the weight of the slab go? It goes into the composite section. So in this case, my M slab goes to composite. Again, if I apply any dead load or any live load, they both go to composite, right? So the only difference between the unshored and the shored construction is how much of the total load is carried by girder and how much is carried by the composite action. So in this case, the girder actually carries its own weight and the weight of the slab. In this case, only the girder carries M naught, that's the self weight, and everything else is actually carried by the composite action. In both the cases, the total load is still the same. It's M naught plus M slab plus dead load plus live load. So the total load is still the same for both the cases. The only difference is how it's distributed between the girder and the composite beam. Okay. Okay, before I write the equations, so let's say if this is my girder, this is my centroidal axis of the girder. So anything with a subscript G means it's only the girder, and anything with ends with a subscript C means it's the property of the composite section. Let's say if this is my location of the centroid of the pre-stressing strand. Since I am calculating the distance from the centroid of the girder only, this is my E0 G. Okay. This is my YTG. This is my YBG. Similarly, I have one ICG, I have ACG, then I have ZBG equal to ICG. I'm not going to write all this. Yeah. And then on top of it, what you have is your composite slab. Once you have the composite slab on it, you'll change the location of your centroidal axis, and it will move up. So this is the centroidal axis of the composite section. Now, for the composite section, this becomes my YTC. This becomes my YBC. And one extra term that we define is Y prime TC, where Y prime TC is the distance to the top of the girder from the centroid of the composite section. So Y prime TC is simply YTC minus the depth of the slab. Okay. Now, if we look at the stress conditions right after, not right after stress, sorry. Yeah. In case of right after stress transfer, in both the cases, do I have the slab there? In either of these two cases, do I have the slab right after the stress transfer? Like you construct the pre-stressing, like you construct the girder, you apply the pre-stressing strand before you, of course, cast the girder, and as soon as you cut those tendons, do you have the slab on there? Do you have it?
The slab?
You said.
I said, yeah, no, yeah.
Okay. So no matter whether you have unshored or a shored construction, at right after the stress transfer, you don't have the slab at all. So in that case, the only thing that you have is the girder itself, its own self weight, and the initial pre-stressing force, right? So again, if I write the equation for sigma top of the girder, this is the initial pre-stressing force Fi over AC G, because right now I only have the girder, I don't have anything else. 1 minus E naught G divided by KBG. This is top, so M min divided by ZTG. So since I only have the girder, you don't even have to worry about any of the composite section or the slab or anything, because you haven't poured the slab on top of it yet, because this is right after you cut the strands. So this equation is actually exactly the same as what we had for a non-composite beam, because at this point the girder actually doesn't know that it might have a slab later on or it might not have a slab later on, right? So this equation is exactly the same as what we had earlier. The only difference is we add a G everywhere to make sure that, okay, we know that, okay, it's the girder only. So again, if I rearrange this, what I get is my equation number 1, and that equation is E naught G less than equal to, yeah, it's KBG plus 1 minus Fi M min minus sigma Ti ZTG. What is M min in this case? M min is nothing but the moment due to the self weight of the girder, because there is no other load acting on it. So this is simply M naught of the girder. Similarly, I can write the stress at the bottom, and this becomes Fi ACG 1 minus E naught G over KG minus M min over ZBG Actually, I forgot to write something. And this is top, right? This has to be greater than equal to sigma t